I did the one thing you're never supposed to do when this is happening. I went to the grocery store. I had to go to two grocery stores actually. Well, the grocery store and the Target store. And the Target store had nobody running their cash registers. All they had open was the self-check. The line is literally across the store.
Oh, jeez.
And it was, so anyway, kind of frazzling, but anyway. Yeah. Has everybody got a chance to sign in? Here, I'll send this away. And again, welcome to the first meeting of the new year, and happy New Year to everybody. Hope you had a good holiday, and hope you're ready for the next year. I know I'm having a very hard time getting back into the swing of things, and every year it's even harder. So I've been having a tough time. But anyway. Announcements. Let's see. Any announcements from anybody? Or,
Yeah, just want to remind folks, they haven't done to,
and I have not sent out that email.
renew, membership.
And I have not sent out that email yet. I definitely get that. Do I have a list of the people who are not?
It was in that set of files that was sent out last week.
Okay.
You need to,
Yeah. This was my first week back to the salt line, but back to the part of my job where I actually have to deal with other humans. And the other humans that I'm dealing with right now are in the midst of a sort of existential crisis, so that's been taking a lot of my time, but that's a different topic. So yeah, anybody wants to re-up, please do so soon. We have a new member with us. Arnold, do you want to introduce yourself?
Yes, I'm all for it. I just got back Monday from 2 weeks, and this is not fun.
Well, brace yourself. 'Cause, it's just going to get... I actually always sort of enjoy cold weather. I don't know, maybe it's anomalous or something, but the low numbers don't scare me too badly. I don't like having to drive with other people when it's like this. It's like too much craziness. But anyway,
Arnold, you said you have any also.
I got a Swiss-on NASCAR 8.
Very nice.
and nice quote.
I had no idea.
We talked to you.
Yes.
You're in the right place.
We boldly go where no one knows what we're doing. Okay. Any other announcements? Any club news?
Christmas party is scheduled for December 6th.
All right. So we're a little ahead of the game here.
Same place.
Same place.
And I thought that was a very nice. That was a very nice location. So we'll look forward to that. I got a call from Justin, actually, as I was on my way here, who asked about clarifying whether 8 o'clock, and I know we're getting a little ahead of the game here, but Justin, I think, wants to get this settled in his mind, for public nights during the summer. And again, just by way of information, we do public nights periodically throughout the period of the year when people actually come out and it's not so cold. So we don't do them, I guess we start doing them in March again. So it's always a continual sort of crapshoot because it depends on the reading and that sort of thing. So I'm not exactly sure what to tell him about that. It seems like the starting time to me is hard to pin down too far ahead because it sort of depends on when the sun's going to go down, right? Because we have to be dark before we can really do much of it. I mean, the ideal for me seems to have the starting time be about a half hour before sunset, basically, so we can get people out there, or, those who are going to come and organize, give them a little dog and pony show, what we do, who we are, all that sort of thing.
Right at sunset.
We're even right at sunset, and then they can come and, look at the scopes and all that sort of thing. So, my inclination is that I know this is probably not going to be what Justin wants to hear, since I think he really likes that time attached to things, but my inclination is that we kind of, sort of set up floating time on that, but, I just wanted to kind of get thoughts on that.
I would agree with
With me. Yeah.
The thing is, you always put it on, it's on the web, not the website, but it's on the website too, but I mean, there's plenty, I mean, we're astronomers, we know that the Earth goes around the sun, and we know what time sunset is.
Yeah,
But
yeah.
you can always just set the event for, 6:30 or 7:30 or whatever time, put it on the calendar.
Yeah.
Or
And it's, put it in sunset or whatever time.
Yeah, putting in something like that, and maybe just providing a little more information, like come out at this time and then once the sun
Yeah, I
sets.
mean, I don't think you can put just sunset on the calendar for general public, because they're not necessarily gonna know kind of where they're at. I mean, they will sort of, but some people,
Right.
people can be amazingly not on things.
Yeah. We had a little talk about a related conversation on the last board meeting about when we make decisions about, or who and when we make decisions about whether public is gonna happen, because frequently, as we found out, all too frequently, it clogs up, and, that means we have to make a decision on that, and so, I think that factors into all this as well. I guess, I'll catch back up with him and kind of pass along some of these thoughts, but, if anybody has anything else they want to.
I think a problem with the summer is if you start it before sunset, it seems like in the summer it takes extra long to even get dark, even if you start at sunset.
Yeah, and I mean, there are days when, some midsummer days where it's really not dark enough to actually see anything until 11 or so, so.
Mm-hmm.
I mean, obviously, we can't do anything about that, the Earth rotates at the way it rotates, but, I think at least we can kind of keep to some kind of schedule. Anyway, I'll catch back up with him and then, pass that information and relay some of this stuff to him as well. This is likely to come up probably at the next board meeting, so. Let's see.
Everybody got their list of, open house space closing right now.
Yeah,
Russ put together.
yeah. And Russ very wisely put together a little computer program that kind of helps us with calculating, and it's really cool. I actually been running it the other day, kind of playing around with it. Because it seems like it would be useful for planning, observation times, because it'll tell you when things are memorized and stuff, and that sort of thing. So we know the times for potential Saturdays all throughout the year, basically, at least throughout the year. So, we can kind of use that as a consultation as well. And as always, of course, we need volunteers at these things, so if you are so inclined, I guess the first one will be coming up here sometime in March. All right, anything more on that? Updates. Anything we need to say about some of the pending issues? Tom,
One thing, the roof mechanism, the extension mechanism is all core now. So, rather than roll the roof all the way out, we can now roll it out to the end of the wall, that's as far as we can go. But yet that will get you down to about a -10-degree declination, so you guys still got that sky. And I want to leave that in place, and I'm going to try to do another extension. I've got, the system we got to roll off Kessler, I've got the date for under of that. It's already here, and it's in the observatory. And I don't know when we're going to get all that put together. It may require us to run electric line through conduit out to a station out near the end of the rails.
on the other end, on the outside?
Yes. So, and we'll just have that set up same way we got together. I don't think, it's gonna be harder to do it down the center because we don't have any structure there in the center, but we could do that if we had to. I'm just gonna try it off of one side, off the west side first, see if that works. This is gonna depend on warm weather, warm enough to get this done. I'm not gonna go out here, January 11th.
Yeah.
So we may be stuck with the short road opening for a while.
Well, the other night when I rolled it out, I think maybe being a little too cautious, but, I didn't want to make a 90-minute drive out there to fix all this stuff. Well, it's 90 minutes out, 90 minutes back, so. I may be out of the loop for at least another week on doing, stuff, just because it's the beginning of the semester and crazy people.
The other quick announcement is the NATO training program I got set up for Tuesday may have me delayed depending on how much snow we get, and if we can't roll the roof off, no sense in bringing people out, so.
Well, that still is on my list to make it out there, so if it happens and I can travel, I'll certainly try to.
If we can get it done, we'll do it. If not, I'm gonna probably make an evaluation Sunday, so they can send out another. Well, there's two of them for sure. Should be three. And then Dave said he was just gonna try to come in from Colorado. I thought, no, that's been a long drive. But I think he's got some other plans too. And perhaps.
Well, the ones that are still active are the two young men from KU, right?
Yeah.
And then is it the young woman from K-State that's still involved? I know there was a student from Washburn.
Yes.
She kind of dropped out.
Yeah, right. Yeah.
Okay.
Yeah, she got her solar one done finally. It was kind of bumpy before we got that finished out, but she got her solar one done.
Yeah.
But I'm rethinking the amount of time that they need to have before I release them to their roles.
Yeah. Okay, Russ, we need to say anything about the relocation, there's probably not much in the way of news on that.
I haven't heard anything, but
Okay. Again, that's where most is probably know that there's a meeting working on planning, hopefully executing and relocating the tunnel, but I think right now there's nothing too good. I did talk to, I think I may have mentioned this to relocation committee members. I did talk to the construction science or whatever they're called, construction department at MTC, Manhattan Technical College, which is a kind of low-tech junior college kind of thing, and they just flat no time. So, if anybody thinks of any other possibility like that, or we might be able to kind of trade experience for labor, let me know. Or let us know. Unfortunately, the one I did was straight now.
I'm assuming Bob Electric and all that is going to be alcohol.
Yeah, well, I thought it was a least worth a try.
Yeah.
And it turned out to be barely worth it. All right, anything else? Okay, well, on with the program then. Should we go ahead and cut at least some of the lights, or you guys will cut out with the lights? Keep us awake. All right, so I want to talk about a couple things tonight. One of them, and there's actually a little bit of method to this madness, and this is actually something I've been meaning to sort of take to the general membership, so it has to be a good time, but I want to make sure, and since we're kind of starting a new year and we had elections and all that stuff, and I'm still here, maybe sort of revisiting how these meetings are run. And I've kind of settled into this format of talking about some subject and then a longer presentation on another subject, which is what I'm planning on doing tonight. But I'm always looking for input and ideas and volunteers. Looking very favorably. Anybody wants to taking over one of these meetings. But if you've got any of that and anything like any suggestions you might have, let me know. tried to mix up the topics a little bit. Some of them were, pretty straight science, some of them were a little bit more conceptual. I tried to do a few things that were sort of hands-on. We've had people demonstrating the equipment, and then I think all those are really great things to do in our meetings. Kind of looking for ideas. But tonight I want to do a couple things again. First of all, as I've done a couple times, I'm going to talk about Constellation. I generally try to pick one that's fairly prominent or becoming prominent at the time of the meeting. I picked this one, which is, by the way, almost an exact copy of one I did about 2 years ago. So if anybody was at that meeting, you might start hearing a little echo in the room. I sort of picked it for a reason, though, and so it's a little bit of a repeat, a rerun. And then, finally, for the presentation, I don't know if anybody's noticed this or not, but for about the last several meetings that I've done, I've kind of been picking things that are in the solar system to do. And I had this sort of grand scheme of starting in the solar system and kind of working my way out. So we talked about things like minor planets and moons, and I thought, well, if you're going to talk about the solar system, you probably need to, begin literally at the beginning. So, space and time. So, I'm going to talk a little bit about the sun and try to place the sun in sort of context of how stars work and how stellar evolution works. So, it's kind of where we're going to go tonight. Before we do that, though, this slide usually comes before that. I guess I got things out of order here. Here is our upcoming events. Of course, these are all general meetings because we haven't got the times posted yet. But these are our general meetings through May. As again, just I'm sure everybody knows, it's the third Thursday of the month that the meeting takes place. So you obviously know about this one since you're here. Next one will be on February the 26th. I thought this slide completely out of order. I wanted to talk about a few news things too. This is another thing I kind of want to do is talk about things that might be of interest. And this is one that I'm really looking forward to. I know many of you that know me or have been listening to me for the last couple of years now. I'm really into the space program, right? I actually applied to be an astronaut and was obviously turned down, but I at least made it far enough to go get the physical, which is a very unpleasant process. You ever see that movie, The Right Stuff? Yeah. It's not that far off. They didn't do the thing where they electrocute your thumb, but boy, just about everything else, you are poked and prodded in ways that is quite remarkable. I found out my thyroid doesn't work quite the way it's supposed to, and I was shown the door, but I suppose if they've got the option of picking physically perfect human beings, they're going to. But anyway, I've always been kind of a fan of the space program. So this is something that I have a really hard time with the fact that this is getting so little attention. And I know there's a lot of stuff happening in the world right now, a lot of stuff. But, not that there ever isn't, but, in particular now. But the launch window for the Artemis II mission opens on February 6th. That is, I believe, 2 weeks from tomorrow. The mission profile for the Artemis II flight is a circumlunar flight. The Artemis II spacecraft will travel to the moon, make a little loop around it, and come back. The reason why this is pretty momentous is that it's been, last crewed manned flight to the moon was in, I believe, 1972. So it's been quite a large number of years. I was 12 years old when that happened. The very first human flight to the moon was in 1968, and it was somewhat similar to the Artemis II mission. It was a circumlunar flight that went out and orbited. And I really love, for that reason, I really love this picture. Of course, this is the crew of the Artemis II. Looks a little different than the way astronauts looked back in the 60s, which I think is a step in the right direction. But I thought I like this picture here. This is obviously a Photoshop. This is not, anything that actually happened. But this is the Artemis II crew and the Apollo 8 crew together. These are what they look like at the time of the flight. They're all passed away now. Jim Lovell died, I guess, 5 years ago. So he was the last of the Apollo 8 crew. And then if you look at the background, you see the detail. There's the Saturn V booster right there that would have taken the Apollo crew. And then over here is the SLS, or whatever they call it. That's the Artemis II booster. So I'm looking forward to this. I think this is going to be a pretty amazing thing. And I hope that, as I said, that when launch window opens on the 6th, that doesn't necessarily guarantee that the launch will take place then, but that's the first day that Earth and the Moon are properly positioned to go ahead and start this. So I know I will be glued to my TV or whatever to kind of watch this happen. I'm super looking forward to it. Here's some other news. This is one that I was kind of pleased to see. The NASA budget is not as bad as was feared. There were rumblings when the budget, whatever they call it, a presidential budget reading or something happened, that NASA could take some huge hits. I mean, numbers in the double digits of percentage, so large double digits of percentage were being kicked around. Turns out that at least for now, that particular bullet has been dodged. This is pretty good news, not just for space science, but for science in general. So that was a positive piece of news that I ran into. And one of the things that survived, by the way, is the Near-Earth Object Needle Surveyor. This, of course, relates to some of the things that we do here in the club. One of the major club observation activities is needle follow-up. And this particular system will kind of be something that may result in targets that are going to need to be followed up on. It had been cut at one time, now it's not cut, uncut, whatever it's back in the queue. This is what it'll look like. It's a relatively small satellite. As satellites go, it's a relatively cheap one. Relatively cheap, meaning only a couple $100 million. Aerospace is incredibly expensive. One of the things I've done in my career is work, at least me and like 300 people on planning satellite missions. Holy cow, you can't believe how expensive this stuff is. And this is actually will relate to the planetary defense idea, which again is something we have our members here who have been working on the Tomahawk relocation have been seeking funding from this office essentially to move that telescope. So I like this, their motto here. And I think I had one Latin class back in high school and really sunk at it basically. But from what I remember, this is sort of grammatically incorrect, but it basically means we're here to save the day. And so this is my attempt to apply to that. It means the day is saved. So hopefully with the new, I don't know, you know, probably know a bit of Latin, don't you? You know, from law.
That sounds about right.
Is it? Yeah. So anyway, so the day is saved at least for the NASA project for now. All right, here's some not so good news, and this is one that I took a little personally. The NASA has decided, due to budget cuts, this is not something I think they thought up on, to close the Library of the God of Space Flight Center, which, if you're familiar with the NASA geography, the God of Space Flight Center is located in Greenbelt, Maryland. It's one of the kind of suburb of Washington, D.C. And it is where Earth observation and climate science are done at NASA. They are mainly done at God of Space Flight Center. My career has all been all about using Earth observation to parameterize climate models. So both of my academic interests kind of flow through Goddard. I've spent a couple of periods of time there as a visiting scientist, and their library was magnificent. I mean, it's just incredible. It was better than the Library of Congress for this one narrow area of interest, and now it's going to be closed. And I don't know what's going to happen to the collection, but I mean, it's just tragic to me. So I was rather upset to read this. This was by the same author, by the way, that wrote that kind of upbeat article about the NASA budget. Here's one that kind of, like a lot of things, kind of has to notice. NASA launched this probe called, actually SpaceX launched it, but it was a probe called Pandora. And Pandora is a small sat, which means that it probably only costs about $70 million, which is dirt cheap by satellite standards, right? But it was a mission to look at the atmospheres of some exoplanets. This is actually a kind of proof of concept of a larger mission that's going to fly probably in about 3 years, I would guess. that's going to enable you a much larger and more systematic survey. So what this little satellite does basically is it's going to observe transiting exoplanets, right, cases where exoplanets just pass in front of their star, analyze them in regions of the spectrum that are at least, as far as we know, associated with chemical and biochemical processes, right? So basically in the visible, near infrared part of the spectrum, which is exactly the same regions that we look back down on the Earth. This is again what I kind of do for a living, is look at these very same wavelengths, but down instead of up. And analyze the contents and characteristics of their atmosphere. This is really super incredible science to me because, you know, it's just tiny little fraction of all that light that went through the atmosphere and it's removed from the effects of the satellite and all that stuff. Pretty amazing stuff. So this thing will be, it's currently launched, it's in orbit, it's properly positioned. I believe they're probably doing a beta test on it. And it's estimated to have a life of about a year. So I think this is, I'm really kind of looking forward to what they start finding with this. And this, of course, the reason why you analyze atmospheres of exoplanets, other than scientific curiosity, is major indicators of life, right? If the atmosphere shows signs of chemical disequilibrium the way the atmosphere of the Earth does, that's a pretty strong argument that maybe there's some kind of biology going on there. So this is, I think, super exciting stuff. This is one that kind of I found just today. In fact, this is from UC Riverside, the University of California, Riverside. Scientists there, some researchers there, have studied the impact that Mars has on the Earth's climate. Again, I'm kind of back in the midst of time of climatologist, so this is kind of caught my attention. And what they found was that there's some evidence that even a tiny, tiny little bit of gravity that Mars exerts on the Earth is enough through time to alter the shape of the orbit in a way that may have some long-term effects on climate. I can't say I was totally convinced. I haven't actually, I gotta confess, I haven't actually dug out papers on this. But based on what I could read in the popular canon, you know, I'm not going to jump on this bandwagon just yet. But I thought it was a really interesting, again, a really interesting thing. And you don't think Mars is going to affect the climate of the Earth, right? And if Mars is affecting it, shouldn't Jupiter be doing it too? Because Jupiter is further away, but it's way bigger, right? Way more gravitational influence on Venus or anything else. So it kind of opened into my mind a way of thinking about the climate system that I had never really thought about before. So I was really struck by that. And thought I'd pass that on. Okay, so those are some news items that kind of caught my attention through the month. Now to the sort of focus on it. Like I said, I'm going to do a constellation that I did some time back, and that's Canis Major, right? The big dome, basically. It's kind of coming into view now a little bit more prominently. It's one of the things serious, one of the things I kind of look for when I look at the sky. And I do have a reason for choosing this. Hopefully it'll come clear and it's related to the next thing I want to talk about. Hopefully that'll come clear as we go along here. So, usually when I do these things, I kind of like to talk a little bit about the origin story of all these, which is related to, in many cases, to mythologies. I had a class on mythology when I was an undergraduate, one of those classes they make you take because you can't sit in the lab all day, basically. I went to. So I took this class on mythology. It's actually pretty cool. I still have this book about it that I pull off and read every once in a while. So this is where a lot of this comes from. But the idea, the Canis Major story is, in some ways, pretty straightforward, right? In terms of how you find it, it's pretty easy to find. I'm not a great finder of things in the sky, you know, it's one of the things I always like about Jan. I go out and listen to her. Oh God, it all makes so much more sense to me now. But this is pretty easy to find. Basically, you just kind of connect the dots of the Orion's belt, and that leads you to Sirius, which is kind of easy to see because it's by this star in the sky, right? And it's a part of this constellation, the big Canis Minor, which then figures it in the story as well. It's a little bit harder for me to find, but I kind of find it basically by finessing my way over from the other end of Orion. Orion is one of the few constellations that actually looks to me a little bit like what it's supposed to be, so it's an easier one for me to kind of keep track of. So this is what the sky would look like around here at 8 p.m. in late February, which is about an hour from now. But you kind of see this a little bit now. So the myth behind this sort of also serves as a little bit of a philosophical story, which a lot of mythology does, right? But the dog in question here, the Canis major, the big dog in question here, is this mythical dog Leleps. And Leleps's quality was never failed to catch its prey, right? It was the hunting dog that never failed to catch its prey. Where the philosophical, I guess, or conundrum part of this is there's also a mythological creature called the Temesgen fox, which is a fox that never fails to escape its pursuer. And so these kind of represent sort of a irresistible force, immovable object conundrum, basically. And it comes across that way in mythology. There's this constant interplay between these things. And in the myths, essentially the way that this was resolved, right, the gods resolved this, was to put them both up in the sky. This is kind of a familiar theme in a lot of mythology, right? And basically let them go about their business, right? And that's where the origins of several of these constellations are. So there's Canis Major, there's Canis Minor, which represents the Temesgen fox, and this one is always chasing this one, and of course Orion and Hunter is around it as well. So that's the mythological story behind at least the one that I found in a little book of myths, or big book of myths about this. You do see this from time to time in places other than mythology. I thought this was super interesting. There was actually a wine named after Leleps. I wonder, people, I will preface this by saying I know next to nothing about wine. I know that the better wines are not the ones you screw the cap off of, so, but beyond that, it's all pretty, it's all kind of, I like wine. I've drunk wine and it tastes good, but as far as being, as knowing much about it, I'm not sure. So, so I don't know anything at all about this particular vineyard or this particular wine, or whether the people buy it, whether there's this picture of a dog with stars all over on it, but I thought it was pretty interesting. I'll also preface this by saying I don't know anything about harmonica playing, and I know as much about harmonica playing as I do about any other musical instrument, which is nothing. But apparently there's a harmonica called a Leleps harmonica, so take that for whatever you can read into it. I have one friend, faculty colleague at K-State, who was a harmonica player. He used to play the harmonica in a band they called the Red State Blues Band, which I think is no longer in business, but they were pretty fun to listen to. His harmonicas are Honors, and I asked him about this brand, and he didn't never heard of it, so maybe it's not one of the major ones, but anyway. So it does kind of, the name though has crept a little bit out of the mythology and star stories and into real life, I guess. Well, as far as why, again, I've kind of thought about Canis Major, there's a couple things I wanted to sort of talk about here. So here's an outline. It does actually look like a dog a little bit. I mean, it looks like a dog that I will draw, or a child will draw, or whatever. But it has some pretty interesting stars in it. Of course, one of the more interesting ones is Sirius. It has some other stuff in it too. Some pretty good deep sky clusters, right? This is still not settled as far as I can tell, but it has this thing called the Canis Major overdensity, which is not exactly a term that rolls off the tongue, but it's basically a region of more stars than seems like should be there. And there's been an idea drifting around or floating around for a little while now that may actually be a dwarf galaxy. And if it is, it's the closest one. I mean, right now, based on my understanding, the closest dwarf galaxies were the Magellanic Clouds, which you cannot see from the northern hemisphere, so you don't see the Angelini Clouds, you're going to go south. This would be, I gotta confess that I did not follow up on this to see if there's been any new news since the last time I talked about this, but it does kind of, it is kind of interesting thing. You notice it's associated with this kind of stream of material, basically, as if it's almost been leading stuff behind, maybe into the gravitational influence of the Milky Way. So there's Canis Majoris Sirius. The name basically means the scorcher, or the one that burns, or something like that. It's a bright, very, very bright star. Actually, 2 stars. One is an A-type star, so if you think back to the, the classes of stars, A's are the big hot ones, right? And then there's a companion, it's a double star, so Sirius B is a white dwarf, it's a D-type star. And I want to kind of point that out because in a minute I'm going to talk about stars a little bit more detail, particularly the sun, which falls into a particular spectral category. So I wanted to kind of get your mind on thinking about spectral categories of stars a little bit. I always like Sirius because it's, it's quite easy to find it. I appreciate that. Here's the other star, though, that's really interesting. And this one's not so easy to see, actually. It's kind of a little obscure, actually. This is where it is in the constellation under Sirius right there. This is VY Canis Majoris. The fact that it's VY tells you that it's pretty dim, right? At least usually pretty dim. The reason why this is interesting is it may be the largest star ever observed. Again, that's open to a lot of debate. But what's not open to much debate is the fact that it is really, really huge, right? Look at this radius scanner, about 1,420 times the radius of the sun. So the sun is not a small object by any means, although we're going to get into that here in a little bit. But this thing is absolutely huge. It's not very warm as stars go. 3,500 kelvins is not particularly hot for a star. For example, the sun is about 6,000, 5,000 units, somewhere in that vicinity. So it's considerably cooler. It's a large, red, super giant star, but it is just absolutely huge. If you scale to our solar system, this is about how big it would be. So there's the orbit of Jupiter right there. There's the orbit of Saturn. It's bigger even than that. And we send out a fairly long way towards the orbit of Uranus. So if this were in our solar system, we would be inside it, basically. So it's just this absolutely enormous star, red hypergiant star. And it would probably look something like this, right? It would be a rather disturbing looking object. I don't know, if I saw something like that in one of my nightmares, then that would be pretty disturbing to me. But that is a very interesting object. And
This is not a carbon star?
I think it's a carbon star, actually. I don't know. It's a red supergiant. Are they mostly carbon stars? I know there was a big spate of interest in carbon stars not that long ago. In fact, AAVSO had a campaign of trying to get amateur observers who have the capability of collecting spectra to look at carbon stars. So it could be. I can look into it. So anyway, I wanted to talk about those things because just as a way of kind of getting us thinking a little bit about stars, and we'll start off with, so we talked about really big weird star here and really big not so weird star, and that leads us to talking a little bit about the sun. So for the main presentation, I want to again talk a little bit about the sun. And I had this book that I really like about the Earth, and I actually bought it in an airport to entertain myself on a flight once and thought enough of it to keep it. It was called The Earth, an Intimate Biography. And for some reason that title was always stuck in my mind. But the intimate part always struck me as being a little weird. So I wasn't gonna echo that piece here. So we'll just call it a biography. Okay. So let's meet the sun a little bit. Again, most of you, I'm sure, being people with interest in astronomy, you know a little bit about this. You've probably looked at the sun hopefully through safe telescopes and all that sort of thing. one of the things that you often hear said about the sun is that it's really just sort of a blasé star, right? It kind of begins to get disrespected a little bit. There's actually a little bit more to it than that. So my goals here, I guess, are twofold, maybe a couplefold. One is to maybe push back against a little bit against this idea that the sun is a completely, run-of-the-mill star. And secondly, to talk a little bit about how stars work, because it's sort of an interesting thing. Stars, in a way, at least in my mind, are sort of the building blocks, basically, of the larger astronomical objects. So, worthwhile to know a little bit about it. So, what about the sun? Well, here's just a few kind of statistics on it, right? I know whenever I show something like this to my students, I see the idea start to glaze over a little bit. Radius of the sun, about 700,000 kilometers. Mass, about 2 times 10 to the 30th kilograms. Pretty hard to relate to that. Those big numbers like that. Spectral class, talked a little bit about it. It's a G-type star. And we'll see kind of where that fits into the star family here. But it's a G25 star. This is the one that's, I think, of the 4 things I listed here, the one that sort of pops out to me the most. Its metallicity is actually relatively high. And that tells us something about, a little bit about how the sun came to be, right? Metallicity is it's basically the ratio of, let me make sure I get this right, it's the ratio of iron to hydrogen in the star, right? And the reason why it's called metallicity is that in astronomy, any element heavier than helium is a metal. That falls that does not align with the definition of metals from chemistry, for example. Chemists say metals, anything that will conduct electricity, right? But what it tells you is that, in the primordial universe, it was pretty much all hydrogen and helium, right, that created in the Big Bang. That's all it would have been. So the very first generation stars formed had been just dominated by hydrogen and helium. And then they made, through this process of nucleosynthesis that we'll talk a little bit about here, started making heavier elements, right? That's where heavy elements came from. And then even heavier elements come from very large stars, and even heavier elements come from things like supernova and all that sort of thing. So if a star like the sun has a relatively high metallicity, high metal content from Earth, that tells you it was formed by material left over from previous generations of stars, right? So this is a generation, actually 3 star. When I was in college, we only had generations 1 and 2, so something changed in that period of time. But so it's a star that formed from the remnants of previous stars. And that's probably plays into a role of why we're here, right? All the elements that make us up were made out of the same stuff the sun was made out of. And all that stuff is left over from previous stars. So that's the thing that always kind of pops out to me when I see these different things. What the sun sort of looks like from the inside, right? It's actually has a relatively complex internal structure, which you kind of expect. At the very center is the core where all that thermonuclear reaction happens. That's where hydrogen gets converted to helium and lots of energy, and then later will get converted into heavier elements and so on. That all happens way down deep in the core of the sun, where temperature is just unimaginably hot, millions of degrees, which is what it takes to fuse together hydrogen, right? We always hear a lot of hydrogen fusion being used as a way of generating electricity, and it's the technology that's been 10 years away forever. But the big problem is that it's hard to generate the kind of pressure and temperature you need to squeeze together hydrogens and control it. We can uncontrol it. That's what a nuclear bomb is. It's uncontrolled fusion of hydrogen, but controlling it and not decimating ourselves in the process, that's a tricky undertaking. So anyway, this is the layer in which all that energy happens, and this is very, I know this is a very thumbnail sketch of all this. Then that energy kind of through processes of diffusion and convection and various other kinds of physical processes works its way up to the surface, and the surface of the sun is the surface we can look at is called photosphere. And it has a radiated temperature, like I said, about 6,000 Kelvin. It takes quite a long time for that process to happen, by the way, that total transport of energy up from the core to where it's eventually radiated out into space takes hundreds of thousands, possibly a million years for that to happen. So it's not a fast process by any means. But anyway, this is kind of the anatomy of the sun as it is now. It hasn't always been that way. That's one of the things I want to kind of get into here a little bit, is what might the sun have been like at times in the past, and what might it be like at times in the future as well. And use it as an example of how stars evolve and how stars work. And that's kind of one of the things I want to work to tonight. So I mentioned that, the sun gets a lot of grief, I guess you could say, or disrespect, however you want to put it, dismissal as ordinary and boring and stuff like that. This was an article from the New York Times. I don't exactly know when this was published, but I thought it took an interesting twist on that. Because basically it said that, well, yeah, the sun is boring, in the sense that it doesn't really have a lot of exciting habits, I guess you could say, which is good for us, right? If you're trying to live next to a star, you don't want that star to be constantly erupting out into space, getting brighter and darker, and doing all kinds of craziness. You like boring, right? It's like living in a neighborhood. You don't want your neighbors to be too exciting. At least I do. But what kind of makes an interesting point here is that quality itself might be a little bit unusual, right? That boring may actually be unusual, might be a little bit rare. So while the sun may be a boring star, my old astronomy professor who was a solar astronomer would, I don't know if he's dead yet, he would be rolling over in his grave if he was, if for me saying that. It's still kind of a nice stable star, right? And that may actually mean that it's a little bit unusual, really. So in order to kind of think about this, you have to kind of go back to the sort of Rosetta Stone of stellar astronomy, which is this thing right here. This is a Hertzsprung-Russell diagram. This is something that gets burned into the mind of every single person that's ever studied astronomy in any way or not. But essentially what the Hertzsprung-Russell diagram does is it relates the temperature of the star that's across the top here, going from low values on the right to high values on the left, and the absolute magnitude. And you do see sort of a relationship. If you start plotting stars into this space, you find that they don't just sort of randomly fall into it, they form a pattern. So that pattern has a lot to tell us about how stars evolve and what the characteristics of stars are. You also see that in addition to the temperature here, this is, by the way, is luminosity compared to the sun. So this allows you to sort of place things in the perspective of the sun. And you'll notice the sun then is right there in this. It's a G-type star, right? That spectral class that we talked about. It has a luminosity of 1 relative to itself. It's exactly as bright as itself. And its absolute magnitude is, somewhere in the 4 something range. And it falls along this thing called the main sequence of stars. And so we're going to spend a little bit of time talking about main sequence stars and what happens when stars start moving off the main sequence. Some of the other ones are a little bit more exciting, right? There's Betelgeuse right there. That's a red giant. You can see that it's a considerably cooler star, but very, very large. And here's the really hot bright ones. There's also a lot of stellar evolutionary information contained in this. Generally, the smaller a star is, the longer it lives, basically. So really big, bright, hot stars, they burn out pretty fast, right? They do not fade away. They go out in blazes of glory, basically. And that would be these ones up here that are extremely hot. So the sun is kind of nicely positioned in all that, right? It's hot enough at the sun, its spectral class is sufficient that it produces a lot of energy. And that's important, right? Because that energy is what drives everything that happens on Earth, including us, right? So there's all this energy to do photosynthesis and all these things, and so the sun is good for that. If the sun were cooler, or a star were cooler, it was down here at as a K or an M, it may not have energy to do that kind of biochemistry. It would do something else, but on the other hand, if it was up here somewhere, that's too much, right? So again, it's maybe a good thing that the sun is a little bit of a boring star. So here's kind of a comparison of some of these. There's the G's right there. That's what the sun is. They generally are somewhere between about 5,000 and 6,000 kelvins for the radiated temperature. Here's a little size comparison, right? So, right here is our sun. There's Betelgeuse right there, huge red star. There's Antares, an even larger one. And so from this, it's kind of, again, you kind of see where people are coming from when they say, well, the sun is as much, right? It's a puny little important star, except that it happens to be ours. Like, I would push back against that a little bit. I guess maybe I would say that, yeah, it is an average star in a lot of ways, but I don't think it's a typical one. And one of the arguments I would put up against that is actually the sun, small though it may be compared to some of these others, and less massive than it may be compared to some of these others, is still more massive than about 95% of all stars. Right? The most stars are little red dwarfs and smaller, cooler stars. So in that respect, the sun is really not that. It has a little bit more size to it than that. It has, I mentioned that metallicity earlier, it's more metallistic, has more metals, has more metals than about 93% of all stars, and that's probably something that we need to start looking for when we start looking for life, right? Because in order for chemistry to work the way we think it needs to work, you've got to have some of these heavier elements, right? So that's another characteristic. And it's also a relatively low luminosity star for this size, which is good because, again, you don't want to be, for living processes at least, you don't want to have a lot of just volatility. That's a great word to use, right? So again, it's a pretty average star, but probably not typical. All right, so let's go through the process here. And again, this is a chance to talk a little bit about how stars work, which is something that's interesting to me, and how stars sort of pass through their life. And so I divided this up into 4 stages, and that's not original with me. It's actually something that came out of a little textbook that I grabbed off my shelf. But understand that this is not for just, this is like a growing person, right? We divide people up into age categories. There's, children and teenagers, and young adults, and older adults, and older adults, and so on. But those are not discrete categories, right? They're a continuum. And stars are kind of the same way, but I'm still going to treat this as sort of discrete steps, but understand that this is a process that actually kind of happens on a continuum. And so stars are born in, at least stars like the sun, are born as a result of actions that take place in giant molecular clouds, GMCs. And it's kind of important to note that word giant there, right? Giant molecular clouds, which there are a bunch of them here, some of the more spectacular looking objects in the night sky. Actually, the kind that would produce a star like the sun are actually a little bit hard to observe because they're not very bright, really. They don't have a lot of luminous material in them. But they're basically just huge, exactly what it sounds like, huge clouds of molecules. If you want to kind of think about the scale of these things, the time scale at which this is going to happen, this at the beginning of the star happens over in a relatively short period of time. So the time that it takes to pass through all these stages, in some cases occur in only a few millions of years, which seems like an unimaginably long amount of time, but really kind of isn't. But we need to talk about this birth stage first. So here's a few things about giant molecular clouds. First of all, they're cold, which is one of the reasons why they're not that easy to see, because material radiates, any mass radiates energy based on its temperature, right? So if something is as cold as a GNC, which they tend to be about 10, that's not 10,000 by the way, that's 10 degrees Kelvin, right? 10 kelvins. So that's just barely above absolute zero. So this stuff is radiating, but it's radiating extremely long wavelengths because of that. The major reason why they can be mapped is because they actually have some elements inside of that are detectable by a Reed telescope, which is one of the ways that these can map. They mostly, as the name would suggest, consist of molecular hydrogen, actually fairly concentrated molecular hydrogen, not super concentrated, but compared to the continuum of space, pretty concentrated, which makes sense because it's referred to as a cloud, right? So about 1,000 molecules, this molecular hydrogen, hydrogen bound together with another hydrogen, per cubic centimeter. So you think about what cubic centimeter is, it's about the size of a dice, right? There'd be about 1,000 molecules of hydrogen. Not a huge number, but way more than what you would find in interstellar space, basically. There's also other minerals in here. This is an important part of this as well. Those minerals tend to be of two types, silicates and carbon and silicon. Think about that for a second, right? What is necessary to have life, right? Carbon certainly is, silicon certainly is. So you're beginning to see where this kind of second generation cloud is going to produce a star that might be associated with the kind of life that we are. Basically. There tends to be some other molecules in there as well. You tend to, again, this is in the clouds that are sort of second generation clouds that are the remnant of a first generation star. Some water, some ammonia, some alcoholides, basically a little bit of alcohol. And also, one of the things that's kind of intriguing is amino acids have been detected in these. Amino acids are the building blocks, basically, of DNA and RNA. I was never much of a biology student, but I remember that, the base pairs that bond together, and that's what makes the DNA molecule. So that kind of suggests maybe a little bit more about how life processes are being kind of, not that amino acids are alive by any means, but they're kind of being pre-staged here a little bit. So that's what giant molecular clouds are composed of, and a little bit of their properties. As I said, at least the ones that form a star like the sun are composed of the remnants of previous stars, the leftover stuff probably from an earlier generation of stars. One of the reasons why some of those things, other than hydrogen, is present in those clouds. Well, initially, the giant molecular clouds are in both thermal and hydrostatic equilibrium. That means that their temperature is uniformly distributed across it, and they are not, the mass is not moving relative internal, right? Which basically means that if you just leave them be, they're going to just sit there, basically. Not much is going to happen. There's going to be this uniform distribution, a continual uniform distribution of material. Right? So in order for stars to start happening, material has to start coalescing, right? And that coalescence has to happen for a reason. And so there has to be star formation essentially has to be triggered by something. This is one of the things that surprised me a little bit when I started kind of doing my homework in order to make this presentation, is that, again, back when I was in college, back in the 80s, we were taught that star formation had to be triggered, and maybe the triggers were nearby supernova, pressure waves passing through the galaxy, maybe the passage of galactic arms, right, that might create a little bit of a gravitational imbalance, and that might start pushing some of the material together. Eventually, those bits of matter would form larger bits of matter, which would have a little bit more gravity, so they would attract other bits of matter, and so on and so on. And I was a little surprised and a little surprised to find out that now, 40-something years later, that's still what the idea is. I don't think there's ever been a real definitive answer to what exactly starts this process. I don't know, anybody know? Has there been new knowledge on this? Because it's been a long time for me. But regardless of that, that's kind of what happens. Something happens in these GMCs to start material coalescing together. And that's really when the action, at least in terms of star formation, starts to happen. So as that interstellar gas and dust, this is a weird little diagram, I know, but as this gas and dust, and notice it's both gas and dust, the dust is kind of important in all of this, starts to collect and cool together, right? Those dust grains become sort of a substrate that the molecules can start to gather on, basically. They get larger, they start having additional gravity, right? Because the gravity of anything is related to its mass, so they become able to collect the particles that are nearby. And things begin to coalesce, right? And as they start to coalesce enough, and notice the size of this thing right here. There's hundreds of parsecs, right? A parsec is 3.26 light years, I believe. So that's big. That's a huge, huge region of space. And within that, there come these little collections of matter. And they're not really stars yet. At this point, they're really not even protostars, even though that's the way they're measuring. They're just more dense collections of stuff. But they are on the way to becoming a star. And so the main source of energy in all this is still gravity, right? There's no luminescence yet. Things are not really hot enough to be fusing or any of those other kinds of energy processes. The energy in this case is still from gravity. These molecular clouds start coalescing together under the gravity of increasingly larger, denser regions within them. They eventually break down into these cloud fragments, right? The cloud sort of breaks up into fragments, subclouds, basically. Takes probably about 40 million years for this to happen. Again, not very long on the time scale here. As these cloud fragments start together, the gravity and the heat generation are opposing each other, so the heat that's generated by that is tending to push them out. The gravity is tending to hold them together, right? So they're forming clouds, but they're not coalescing very quickly at this point. And because of that, this has to happen again in very large clouds. So it takes a very huge cloud to become a star forming region. But this is the steps along the way of this GMC, this cloud collapse stage is a pretty key step along the path towards forming a star. And so we reach a point where these cloud fragments, right, they're inside these remnant clumps of gas, basically. But as they begin to kind of coalesce, now we get a new player in the energy thing. We start to get kinetic energy, right? So these things are starting to move toward each other. Kinetic energy, again, is just the energy associated with motion, right? So this coalescence, this movement toward each other becomes another source of energy. And at this point, these things can start to emit infrared light. Now, this is not infrared light like, near infrared light, the infrared light that the sun is. It's still pretty far out in the infrared part of the spectrum. But it still starts to make these things more observable, right? Because you can, if you've got a big enough dish telescope, you can start detecting these emissions. And then I'm getting a little bit ahead of the story here, but as this process continues, more matter collects in this new burgeoning star. Eventually, the kinetic energy is enough to compress it to the point where nuclear fusion starts. That's getting a little ahead of the game here, but a little swivel order, that's kind of where we're headed here. But we're not quite there yet, right? We haven't gotten to fusion just yet. So the story so far then is we're somewhere around in here somewhere. The prestellar core has started to form, right? We've got this region that's being powered mainly by gravity. It's kind of making it out to this proto-star stage, right? So we haven't quite reached the point where the star is behaving the way we think of stars behave. And one of the phases that it passes through on this has always been a little bit confusing to me because these are referred to as Tautari stars because of the first one ever discovered. Tautari stars are considered a type of variable star, but they don't have fusion happening yet. The energy in a Tautari star is it's a phase in star formation just before fusion starts. So there's a lot of compression, right? There's a lot of gravitational energy. Tautari stars are relatively hot compared to, a stove, about 3,000 kelvins, right? You wouldn't want to get very close to one, but it's not high enough for fusion to be happening yet. So the energy still is still due to gravitational collapse. This is sometimes called the Kelvin almost phase of star formation because of this gravitational collapse. I was a little hacked to hear the word Kelvin because he was the one who proposed that the energy source of the sun was gravitational collapse. Turns out it wasn't, right? Not enough energy can be made, but we'll give him a little bit of a salute for understanding the mechanism that now drives this stage called the Tautari star. This is kind of what they look like. They tend to be very young objects. They tend to be within clouds of material, right? Because they're kind of stars, right? So they're still surrounded by the cloud stuff that they were formed out of. Not particularly easy to observe. There's a Tautari star, a young stellar object. Notice, by the way, where this data comes from. This comes from the 2MASS survey, the 2-micron all-star survey. 2 microns is relatively long for radiation, right? It's a fairly long wavelength. So this is the more energy. These are actually Tautari stars that are probably right on the cusp of fusion. So, what comes next? Well, Act 2 is when fusion starts. And I think a way to sort of illustrate this is to think about this as the star is moving on to the main sequence. It's like going from an infant, right, to maybe a young adult, basically. And so the protostar is not, protostars don't fall onto the Hertzsprung-Russell diagram yet. That's part one here. As they begin to kind of show this coalescence and this compression due to gravitational energy, increased emission of thermal energy, eventually we start to get fusion, and then the star falls onto the main sequence. This is what happens when the process of nuclear fusion begins to happen in the core of the star. And in order to think about that, maybe we have to ask a more fundamental question, basically, which, what is a star? And this is one of the things that was always a little confusing to me, because this is a definition of stars that again comes directly out of the book that I found. A massive luminous sphere of plasma, right? It's a form of a phase of matter that's been completely ionized, all its electrons have been stripped off, right? Held together by its own gravity and generating light and heat through nuclear fusion at its core, primarily by fusing hydrogen and helium. That's the case in our Tautari stars, really stars. They don't have any fusion going on. This is not something I really know the answer to. If anybody does, can illuminate me on that. No pun intended. I would be really happy to hear that. But anyway, that's how we're going to think about a star, right? It's a, paraphrase they might be giants. The sun is a massive incandescent gas. It's actually not. It's a mass of plasma, but it's one that's powered by these nuclear forces. So that's how we're going to think of stars. The other thing we have to kind of come to grips with here is that not all stars are created equal. And you can kind of divide stars up roughly into you can divide the life cycle of a star up based on its initial mass. So this whole birth stage right here, through the cloud, through the protostar, through the Tautari phase, and then into fusion, that's all part of the sort of birth process. Now we have to think about the mass of stars. So if a star has a certain mass, about 8 times greater than the sun, it starts following a different path than relatively lower mass stars, low and medium stars like the sun. So when I was putting all this together, I originally was thinking, well, I'll go down both branches here, but I decided nobody wants to stay here for that long. So I'm just going to stick to this low, medium mass one because we're talking about the sun here, right? So its steps through life are going to be a considerable amount of time as a, like we said, a relatively stable star. What was the word, Gary? That you use for the sun that, I don't remember either, sorry.
That was a long time ago.
Yeah, it was. Anyway, whatever Gary said, that's where we're going with. And then this branch down here is the really big massive stars, and they're actually a lot more exciting when they die. You know, their stars in this case are kind of maybe the opposite of people in the sense that we normally think of young people as being radical and misbehaving, right? And as you get older, you get better behaved. Stars kind of the other way around, at least high mass stars. They start off relatively well behaved and then just go freaking nuts when they get older. Low and medium mass stars, a little bit less spectacular, I guess you could say, but this is the branch that the sun is going to follow. So this is how we're going to do it. So, how do we know what that protoplanet, how do we know what the sun is made out of, I guess? Well, we know because you can measure the spectrum of it and stuff, but how did it come to be made of that kind of stuff? How do we know what that protoplanetary disk was actually made of? It's understood reasonably well, largely because there's still a lot of stuff left over out there that was the protoplanetary disk at one time. And we get little pieces of it falling on us every once in a while. Anytime there's a meteorite, right, this is a carbonaceous meteorite, anytime one of those falls, that's a piece of something that was at one time fairly far out in the solar system, far enough out that the sun couldn't melt it, basically. So it's retained a lot of the chemical properties of that original protoplanetary disk. That's how we know about, that there are amino acids and stuff out there. They've been found in meteorites. This particular carbonaceous chondrite is probably not from this one, but it's probably from an asteroid or something like that. That's something Bennu or something like that. Is that Bennu? Anyway, it's a carbonaceous chondrite. A carbonaceous asteroid will be found relatively far out in the main asteroid belt. So what we have here then is this transition to that protoplanetary state. We get fusion initiated. And in the case of the sun, we settle in because of its unique combination of mass and composition. It has settled in as this G-type star. Its temperature about 6,000 kelvins, and it falls about here in the sequence, right? It's probably been like that for nearly since the beginning, right? There was a school of thought at one time that said that maybe stars had to pass through different structural classes. I think the thinking now is that they tend to kind of fall into a class and stay there through a lot of their lifespan. So the sun has probably been a G-type star for pretty much since the beginning. And its characteristic is that it's fusing hydrogen into helium. That's its energy source. So we should probably talk a little bit about hydrogen fusion. This is a process called nucleosynthesis, right? And it was probably one of the major intellectual accomplishments of science through the previous century. The understanding of how this process worked, which was worked out largely theoretically, but with some experimental input, kind of goes something like this. And depending on the type of star, hydrogen fusion can happen in two different ways. The way that the sun does it is called the proton-proton chain, or the PD chain, which is something that exhibits Snickers in classes, but we won't talk about that. And basically the way it works is you get two hydrogens, right? It just kind of works in parallel to each other. One of them gets converted into a neutron, right? It keeps its protons stripped off. That emits some energy, emits a gamma ray. That's one of the reasons why we know this is happening, right? We can measure, and again I'm using the royal we here, one can measure the emissions of gamma rays and these other weird little particles called neutrinos, and compare that to the theoretical calculation of what should be coming from the sun and match. Right? So again, this is done by basically making huge tanks of cleaning fluid and burying them deep down in mines to try to isolate it from all the surroundings. And every once in a while, very infrequently, we detect one of these particles. But initially what happens is through this chain of process here is we get a helium, a kind of heavy helium, and those fuse together, and the final product here then is helium. All right? Helium is called helium because it was actually discovered by looking at the spectrum of the sun. Helios, right? The sun. Helium, by the way, on Earth was first isolated at KU. I remember my stepson told me that he was a KU grad, so interesting little bit of Kansas trivia there. But at any rate, this is the process that the sun, this proton-proton chain, and it's called a proton-proton chain because these isolated protons that form part of the reaction. This is how the sun does. There's another fusion process that happens in stars a little bit bigger than the sun, or in some cases somewhat bigger than the sun. That's the CNO chains, carbon, nitrogen, oxygen cycle. It's a little bit more complicated, and it really is a cycle that feeds itself. But for the sun, the PP chain, the proton-proton chain, is the operative. So that's where we are now, right? There's the sun sitting sort of in the middle of the main sequence, right? Hotter than the red stars, cooler than the blue stars, a G-type star. And if you look at the internal structure of it, again, this is a simplified view, it's going to look something like that. There's that core where all that fusion is taking place, right? There's that radiated zone where the energy that is emitted comes out as radiation. And then this convective zone right here is when convective processes, mass movement processes take over. You ever look at the surface of the sun through a fundamentally say telescope? It looks kind of like boiling rice, right? You know, it's almost global. And now this little boiling rice appearance is due to the tops of convection currents that are rising up from below, emitting that energy out, and it gets emitted in space through by the photosphere. So at this point, this is a very simplified view of what the interior of a star like the sun, and quite likely what the sun actually looks like. Now, one thing I said that probably the sun has always been a G-type star, but there is an anomaly in it. And that's at one point back in its earlier days, it was actually considerably dimmer than it is now. And this would actually have been, it's imprinted in Earth history a little bit. When I was a climatology student, we came into contact with what was called the faint early sun paradox, which was the Earth was hotter and the sun was colder. And the answer to that had to do with the composition of the Earth's atmosphere as its sort of thing. But the idea of the fact that the sun was a little cooler, not radiating at quite as high temperature then, was a valid one. So while the sun has probably always been in that G-type category, it hasn't always radiated at the temperature it currently is. And again, that's good for life like us, right? Because we sort of need temperatures to fall within a certain range for chemistry. All right, so that's the kind of story so far. I threw this slide into this little table because it sort of gives a little bit of time on this, right? So the time that it takes to go from the center stellar cloud with very cold temperatures up to a main sequence star where the central temperature, right, the temperature of the core there, is about 15 million kelvins, right? To put that in perspective, average day on Earth is probably about 300, maybe 310, something like that vicinity. So super, super hot, but you get an idea of the amount of time that it took to get here. So these are the times that it took. Most of it measured in millions of years. It actually happens pretty fast, really. So the sun probably went from being, a cloud to being a little collection of dust, basically, dust and molecules, to being a main sequence star, probably in about, that would be hundreds of millions of years. So ever since then, which has probably been about 4 billion years, it's been roughly the way it is. A little bit of change in temperatures, but roughly the way it is. There's been a suggestion, though, that the sun and stars like the sun, and therefore possibly the sun, might actually kind of go through stuff, but it actually becomes a little bit less active in a way. So as they stars like the sun maybe start becoming less active, fewer mass ejections, less than sunspot cycles like that. And so there's been speculation that the sun may actually, at some point, enter a stage like this. Probably, its temperature probably won't change. It just won't be as active, right, in the sense of sunspot cycles and that sort of thing. So in a way, it's, it's the opposite of what you think of as a human midlife crisis where people start acting out. It's going to become even less interesting. So that kind of brings us to where we are now, this long period of time where the sun has been doing its thing, right, accumulating helium in its core, but still fusing, mostly maintaining a fairly stable temperature. What's going to happen to it in the future? And this is where we get into kind of speculation a little bit, right? Where here we have to kind of think about analogs to the sun, stars that are like the sun, and also theory, what theory would tell us happens. So, sun's been in action for about 4.5 billion years. It's probably about halfway through its lifespan. So about 5 billion years from now, it's going to start going through some changes again. It's going to turn into a stellar senior citizen. I don't know how accurate this is, or this is your 5 billion years from now, this looming huge red giant star out there. Here's another kind of view of that. Here's our solar system today, right? 5 billion years from now, it might look something like this. It's actually, one school of thought says that the sun could be big enough to essentially swallow the Earth. It almost certainly will swallow Mercury, and Venus could actually swallow the Earth as well. So clearly it's going to go through some changes. Well, what's going to happen to it then? First of all, it's going to start moving off this main sequence, right? It's going to start moving up into this this sort of giant phase. But it's not going to become a supergiant. It would have to be a much bigger star in order to do that. So it's going to start moving into a space kind of over here, cooler and larger, but in some ways less luminous. So it's going to transition to this red giant phase. And, forgive me for the crudity of these diagrams. I'm really not much of an artist, but this is what is thought would happen here. Eventually, it's going to exhaust the helium, or the hydrogen, right? It's going to burn up all the hydrogen. So that core down there where all that was happening is mostly now going to be an inert helium. But there's going to be at least a little region around that core where conditions are sufficient for the helium to start fusing. So helium, and I'll show you that here in just a second. So now instead of fusing hydrogen to hydrogen, now we have helium fusing together. That's going to produce energy, but not nearly as much as fusing together with hydrogen. And so the whole star is going to become cooler, and it's going to start expanding. That's what a red giant is basically. It's a star that has used up all or mostly all of this hydrogen, and is now burning mostly helium. So it forms this kind of cool, extended envelope. In terms of where it is on the Hertzsprung, unless this is kind of simplified HR diagram, comes off the main sequence back towards your comes off the main sequence back towards this red end of it, right, the cooler end of it. And then maybe, depending on how big it was eventually, it will start moving up the giant branch. Now, the sun's not going to be big enough to reach this area, I think. So, helium burning is a little different, or helium fusion is a little different process. It's called the triple alpha process, because an ionized helium is an alpha particle, right? Anybody ever do that thing in high school science class where you make a cloud chamber and then you put a little bit of emitted material and you see little streaks? Sometimes one of those are alpha particles, are basically stripped helium, right? And you make a little track through it. So the triple alpha process is one where two of these alpha particles get fused together and form beryllium. It's kind of it doesn't last very long. It is temporarily there, which fuses to with, sorry, I'm doing this wrong. Okay, two heliums fuse beryllium. That fuses with another helium, that's why it's called triple alpha, right? There's 3 of these involved in it. And the eventual result of all this is gamma rays and carbon. So the end product of the triple alpha process, at least this form of it, is carbon. There's another flavor of the triple alpha process. In that case, the same thing happens, right? You get these 3 alpha particles, they form an intermediate beryllium product. That becomes a carbon. Another alpha particle comes into play, and then you end up with oxygen. So the material left over from this phase is carbon and oxygen. Does that portend anything, right? Carbon and oxygen, that's stuff of life, right? So you can also sort of see here how this process is beginning to make the elements that are going to be incredibly important for us, right? This obviously wouldn't be happening. We wouldn't be the result of this process in our sun. It would be some previous generation, right? But this is probably where some of these elemental particles that underpin life processes came from. So here's a star I kind of mentioned. I think I mentioned this one. This is a star that's probably similar to what the sun is, but a little bit more advanced, right? A little older. So this is Arcturus. So this would be a pretty good analog of what the future of the sun is probably going to be. Okay, so that takes us to the red giant phase, right? And now we reach the kind of end of the line here, the finale of all this. And that's the death process, basically, of a star like the sun. As I mentioned, the death process of a star sort of depends on its initial mass, right? The really exciting stuff, things that blow up and form black holes and all that stuff, those are bigger stars to start with. Something like the sun has a little bit less spectacular ending, but in some ways, I think, a little bit more consequential one. So the next phase then happens when this red giant starts to finally burn out all the helium as well. It doesn't take nearly as long for this to happen. So if you cut through the red giant, you look down into it during the final stage, it's got this core of carbon and oxygen, right? That's the remnant of this helium fusion. There's probably a little bit more helium fusing down in there. There might actually still be a little bit more hydrogen fusion taking place. It doesn't ever really totally stop, right? At least not until the very end. But you probably have a little bit of it. But then there's this envelope of hydrogen around it. That's the kind of it's not hot enough to fuse, right? So it forms this sort of envelope around it, and that's actually the surface that you're looking at. So as this, and again, I apologize for the diagrams here, but I'm not much of a drawer. But what happens is you start to get the red giant, right? There's that red giant star right there. And it starts pushing away some of that material. It kind of forms like a solar wind. It's that envelope of helium that's being pushed out, and pushed out, and pushed out. Eventually, and it happens pretty slowly. These clouds don't move very fast. Eventually, though, the core of this gets exposed. All that hydrogen is pushed away, right? And the core, that remnant of it, gets exposed. And when that happens, it really dramatically speeds up this process, right? So there's this core, there's that core of stuff that was pushed away in the earlier stages. It's even further away now. Now we have this faster moving material, this faster moving gas. As it moves faster, it starts expanding into that gas that was already there, right? And the result of it becomes luminescent, and the result of that is what's called a planetary nebula. So here are a few planetary nebulae. I think these are some of the most spectacularly beautiful things out there, right? But essentially, this is just that envelope of gas around this that was formerly part of the star, got pushed away, got compressed by this more rapidly expanding. And that thing right down in the center there, that remnant core, which you can kind of see in these pictures right there, is the next stage in the process here. It's what's called a white dwarf. So here's a typical white dwarf, about like the sun, will form some 5 billions of years or so from now, compared to the Earth, roughly the same size, right? So its mass, here's the thing about this, its mass is still nearly the same as the mass of the sun. All that material that got blown off and pushed away, certainly massive, but not as much, but the majority of the mass is still there. It's there in the form of this hyper-compressed carbon oxygen, right? So its radius may be pretty similar to the Earth, but its mass is still going to be very similar to the sun. It's going to be incredibly dense. So to give you some idea about that, look at this velocity. This would be the escape velocity, right? Escape velocity is how fast you need to go to escape from the gravity of the body. Its escape velocity, if you were to try to escape from it, is 2% of the speed of light, 0.2 c. To put that in perspective, 0.2 c, according to the back of my envelope, is about 6,000 kilometers per second. The escape velocity of the Earth, how fast, for example, the Artemis 2 cruise can go or get away from the Earth's gravity, is about 11 meters per second, much, much smaller. So extremely, still just extreme gravity. And this white dwarf stage here is kind of the end of the road, basically. It's that stellar remnant. It's thought that at some point, white dwarfs are going to fade to black. They're going to become literally fade to black. They're going to become black dwarfs. I don't know if any of these have ever actually been observed, so this is still just sort of theoretical, but I think it'd be extremely hard to observe because they're not going to be very luminous, but this is thought to maybe be the very end of the process. So eventually, this will likely be the fate of the sun. If we put this all into a cycle of years, from year 1 to about 14 billion years is probably going to be the lifespan of a star like the sun. We're around here somewhere right now. Right? The sun's actually still getting a little bit warmer. It's going to continue to get warmer through several billions of years until it starts transitioning into this red giant phase. And all the way down. So eventually this will be the fate of the sun. Okay, so one other thing I wanted to make a point here, I've kind of alluded to this a few times, but this is one of the things that makes this whole story pretty interesting to me. Right? I don't remember too much about biology from the one biology class I had, but I do remember C. Hopkins Cafe. Anybody run into that? Those things are called little things you used to remember. Mnemonics. Yes. C. Hopkins Cafe is the elements that are necessary for life: carbon, nitrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, so on and so on and so on. All of these are hooked up to stars, right? But carbon and oxygen, well, hydrogen is from the primordial universe, but carbon and oxygen probably came from the carbon and oxygen was contained in the Earth, right? Probably came from the planetary nebula phase of the protostar. And so all that kind of became a part of the giant molecular cloud that was the nursery of the sun. So, biological processes and processes of life harken back directly to some of these processes we talked about. And with that, I will close. Someone did this.
As man once said, we were made of star stuff.
Yeah, we made the star stuff. Yeah. What is interesting to me is that that's undoubtedly true, but there must have been a bunch of different stars because all the heavy things, like iron, for example, as far as I know, has to be made in a supernova. The regular stars just don't get hot enough. And so, you get heavier elements, they have to have been made in a much hotter environment. So, it must have been not just a star that was our ancestral star, but more than one, basically. All right, questions?
So the amount of heavy elements that we actually have on Earth is pretty significant when you think about how much of that makes up the Earth's core. It's pretty amazing that there and so many cycles ahead of us.
Yeah, maybe one of these days, billions of years from now, somebody will be sitting around the table and they'll have stuff in them and it used to be a mess.
You're welcome.
Yeah, it is. I can say that, I hope it doesn't hurt. But,
I'm curious, so we've seen more, at least in my short time here, it seems like we've seen more of these chances to see Northern Lights because we've had more of these coronal mass ejections. We're sort of seeing, we have more opportunities in this part of the world to see. So are we seeing more of these happening?
you know, it seems to be that way. That may be a little bit of a sort of availability bias, you know, things that happen nearer time seem more common, but
Well, I remember, we're at the peak of our 11-year cycle. So every 11 years, we come to see it.
you know, if those people are speculating about the, you know, semi or the phase of less active, then auroras may be one thing that happens. My impression is that's not going to happen, like, you know, next year or even next millennium, you know. But the time scale of these things is, you know, so hard to relate to as a human, you know, where you live, if you're lucky, maybe close to a century, if you're very lucky, which is just nothing on a time scale of that this stuff happens on. So that's a kind of an interesting perspective. You know, stuff's been going on for so long. Anyway, so yeah.
The sun actually has more than just in the 11-year cycle. There's also a 100-year cycle and a 2,000-year cycle. The variation of 11-year cycle and 11-year cycle is moderated by these other two cycles. We just came out of the most recent 100-year low, and we're starting to build back up to more intense sunspot cycles. So over the next few cycles, we should see more sunspots.
People see records of this stuff in tree rings. I mean, I had a picture class in paleoclimatology, and one of the things we did was go to California and drill into these extremely old trees. I mean, trees that are more than 1,000 years old, and pull the cords of wood out and count them with tree rings and look at the size of them and look at the pattern. And you can see it is dead obvious when you look at it that there are patterns in there. I mean, it's just absolutely obvious. You don't even have to measure it just to get to it. It's class. But you didn't really need to see the cycle. And, yeah, you see remnants of these. So I know I had a job one summer working for a guy who was analyzing that solar cycle. So I ended up basically doing statistical analysis of these fitting Fourier functions and stuff to it to try to get an idea of the timing of that almost. Because he had this weird theory about something that I never totally understood. But this guy is one of those people that sort of find an office for it somewhere over the hallway, you know. He was an interesting guy, but I don't think he was right about this. It was an interesting summer of looking at data about things like this. So
There's thought that the 11-year cycle is actually the 22-year cycle.
yeah,
Well, it is the 22-year cycle of the polarity of the sunspots.
yeah. I've seen that. And it's related, at least, their idea that keeping our clocks related to drought cycles. Right? There's a fairly close alignment between, this is one of the things that the tree rings point out. There's a fairly close alignment between that and drought cycles. And sort of negative drought cycles sometimes are reinforced patterns of that. So, you know, we're kind of edging into a mega drought right now in the desert southwest. And the last one that lined up kind of the way the current one is probably resulted. Anybody ever been to Mesa Verde? You know, that was occupied at one time by a relatively vibrant civilization. Then they abandoned it, right? They couldn't live there anymore. Probably because of drought, probably because of super regional drought. And also the people that, you know, the descendants places nearer to rivers, mostly, so like the Zuni and Acoma and all those pueblos that you see, if you pass through Arizona or Hopi, that pass through Arizona or New Mexico, those are the descendants of, distant descendants of the people that lived in those, and they had to, because of this mega, that's a hypothesis that's been pretty well supported, that's been presented. So, yeah, there's actually